For over a century, black holes have been among the most mysterious objects in the cosmos, dark, dense regions of space where gravity reigns supreme and light itself cannot escape. Scientists have long debated what truly lies beyond their event horizons. But now, groundbreaking insights are challenging everything we thought we knew. A revolutionary new model, built on the convergence of quantum mechanics and general relativity, is offering an unprecedented glimpse into what might actually exist inside a black hole. And it could completely reshape our understanding of space, time, and the very fabric of the universe. This idea didn't emerge from nowhere. It's rooted in decades of work by physicists who've tried to reconcile the two great pillars of modern physics: Einstein's theory of general relativity, which governs the large-scale universe, and quantum mechanics, which rules the microscopic world. Bridging these two has been one of the most elusive goals in science. Enter string theory, a framework suggesting that all particles are actually vibrating strings of energy. According to this model, what we think of as the inside of a black hole may not be a singularity, a point of infinite density, but something far more complex. Instead of a mysterious, physics-breaking core, new models propose a structure called a fuzzball. This concept replaces the traditional singularity with a dense mass of vibrating strings. Essentially, a tangled quantum structure that retains information. Matter that falls into a black hole doesn't vanish. Instead, its data is encoded in this tangled mass, protected from destruction. This proposal does more than explain what might be inside black holes. It could finally resolve a decades-old paradox. In quantum physics, information can never be lost. But classical black hole theory suggests the opposite. Once something crosses the event horizon, it's gone forever. The fuzzball theory, however, argues that the information isn't lost at all. It's stored, scrambled, and potentially even retrievable. This changes everything. Black holes aren't just cosmic trash compactors. They may be natural archives, storing the complete record of everything they've ever absorbed. The death of a star, the collapse of a planet, even the remains of once living beings. Each may leave behind a trace encoded within the structure of a black hole. And if that's true, then black holes become more than destructive forces. They become cosmic historians. Structures that don't erase but preserve. More astonishing still is what this means for time itself. Inside a black hole, time behaves very differently. Some models suggest that past, present, and future may all exist simultaneously, frozen in a kind of temporal stasis. In that sense, everything a black hole consumes may remain locked in a quantum imprint, suspended across time. That sounds like science fiction, but the evidence is beginning to align. Recent observations from gravitational wave detectors, along with data from the Event Horizon Telescope, are revealing patterns and signals that defy classical models. Faint echoes after black hole collisions suggest that spacetime behaves strangely near the event horizon, just as the fuzzball concept predicts. These ripples, traveling billions of light years to reach us, carry whispers of quantum structure and internal complexity. They suggest black holes are not smooth voids but layered. Black holes were once imagined as bottomless pits, regions of space so dense that nothing, not even light, could escape their grip. For decades, they represented the ultimate end, the destruction of matter, the erasure of information, the death of all that entered. But today, that image is changing. Thanks to breakthroughs in quantum physics, string theory, and observational astronomy, a new and surprising idea is taking shape. What if black holes don't destroy information at all? What if they preserve it, in ways we are only beginning to understand? The concept of Hawking radiation, first proposed by Stephen Hawking, laid the foundation. It suggested that black holes slowly evaporate by emitting radiation. For years, this posed a paradox. If radiation carries no information, then the contents of a black hole are lost forever, violating a fundamental law of quantum mechanics. But a growing body of research suggests a different story. A radical one. One in which black holes aren't voids, they're vaults. One compelling theory is the fuzzball model, developed from string theory. Instead of a smooth event horizon hiding a singularity, Black holes may be made up of tangled, stringy quantum states, like a giant ball of quantum yarn. In this view, everything that falls in becomes part of the fuzzball. Information isn't lost, it's encoded, scrambled, and stored across its quantum surface. If this is true, it changes how we think about space, time, and the flow of information in the universe. And then there's the reimagining of Hawking radiation. If fuzzballs exist, then the radiation they emit could carry subtle imprints of the information within. Not just random particles, but clues, tiny messages from deep within the structure of spacetime itself. Every particle might tell a story. This leads to a profound conclusion. The event horizon, once thought to be the final boundary of knowledge, might actually be permeable. It might not be a wall, but a veil. A soft shell that holds and releases the past, particle by particle. These ideas have implications that go far beyond astrophysics. If black holes preserve the history of everything they consume, stars, planets, even traces of consciousness, then nothing in the universe is ever truly lost. The cosmos becomes not a destroyer, but a record keeper. This perspective also connects to the most mind-bending ideas in theoretical physics. If the insides of black holes are governed by quantum geometry, they may open portals to other regions of space. Wormholes, once dismissed as science fiction, could become real physical phenomena, bridges between distant places, or even between universes. Black holes might not just be ends, they might be gateways. And far from being untestable, these theories are increasingly grounded in data. Gravitational wave detectors like LIGO and Virgo have captured the ripples of black hole collisions. The Event Horizon Telescope gave us the first image of a black hole's shadow. Future missions may go further, measuring polarization, decoding radiation, analyzing high-energy jets. Soon, we may begin to map the quantum structure of space itself. What we find in the hearts of black holes may tell us not only about their past, but about ours. About how the universe evolved. About what it chooses to remember. About whether the information of our world, of Earth and all its life, could one day persist within the deep vaults of space, long after our sun burns out. This isn't just the study of black holes. It's a new philosophy of being. We're discovering that the universe may not be a cold, forgetful expanse, but a cosmic archive. Every collision, every star, every breath might leave a trace. And if black holes are the memory banks of the cosmos, then we, through our science, our questions, and our curiosity, are the readers of that grand, cosmic library. As we continue to study these gravitational giants, we're not just learning about destruction. We're discovering a deeper truth. That in the darkest corners of the universe, there may be light. Not of photons, but of understanding. And perhaps, in unlocking the secrets of black holes, we'll unlock the deepest